Hi everyone, welcome to Advent of Code, day 22. This video I'll be live coding my solution in Python, showing off how I approach the problem, ultimately, hopefully, come to a solution. Let's get right into it. Day 22, sand slabs. Enough sand has fallen. It can finally filter water for Stowe Island. Well, almost. The sand has been falling as large compacted bricks of sand, piling up in order to form an impressive stack here near the edge of Island Island. In order to make use of the sand to filter water, some of the bricks will need to be broken apart, nay, disintegrated, back into freely flowing sand. The stack is tall enough that you'll have to be careful about choosing which bricks to disintegrate. If you disintegrate the wrong brick, large portions of the stack could topple, which sounds pretty dangerous. Alright, a little Jenga action. The elves responsible for water filtering operations took a snapshot of the bricks while they were still falling. Your puzzle input, which should let you work out which bricks are safe to disintegrate. For example, each line of the text in the snapshot represents the position of a single brick at the time the snapshot was taken. The position is given as two x,y,z coordinates, one for each end of the brick, separated by a tilde. Each brick is made up of a single straight line of cubes, and the elves were even careful to choose a time for the snapshot that had all of the free-falling bricks at integer positions above the ground. So the whole snapshot is aligned to a three-dimensional cube grid. A line like 222 means that both ends of the brick are at the same coordinate. In other words, the brick is a single cube. Lines like 0010, 1010, both represent bricks that are two cubes in volume, both oriented horizontally. Yep, that makes sense. 10 cube brick, this is all making sense. The ground is at z equals 0 and is perfectly flat. The lowest z value a brick can have is therefore 1. So these two are both resting on the ground. This one is above the ground. Because the snapshot was taken while the bricks are still falling, some bricks will still be in the air. You need to start by figuring out where they will end up. Bricks are magically stabilized so they never rotate, even in weird situations where a long horizontal brick is only supported on one end. Two bricks cannot occupy the same position, so a falling brick will come to rest upon the first brick it encounters. Okay, the bricks are arranged like this. Rotating the perspective, you can see how they're arranged in the y direction. Once all of the bricks fall downward as far as they can go, the stack looks like this, where question mark means bricks are hidden behind other bricks. Again, on the side. Now that all the bricks are settled, it becomes easier to tell which bricks are supporting other bricks. Your first task is to figure out which bricks are safe to disintegrate. A brick can be safely disintegrated if, after removing it, no other bricks would fall further directly downward. Don't actually disintegrate them, just determine if, for each brick, only that brick will be disintegrated. Okay. Yeah, this seems hard, but we can get into it. I've also installed a new Neolim theme, so hopefully that'll power us to finding a great solution. Input is pretty big. Let's grab this example too. Oops. Cool, let's get right into it. First, we'll want to parse the input. Where I guess we'll initially store a brick as a tuple of 6 ints. Or maybe it can be a tuple of int, tuple, int, int, kind of complicated types. Bricks could be a list of brick. For line in lines, x1, y1, z1, x2, y2, z2, re find all. We're looking for this, comma this, comma this, tilde, this, comma this, comma this, and that, and then line 0. Then we'll have a little bit of, let's just print these out. This one, or let's just end bricks and x int x1 int y1 int z1, and then a second tuple of int x2 int y2 int z2, and then print the last element of bricks. And find all. What is this mad about? Got this extra. Here, let's clear the screen. And I guess let's also open up the example in another window. Yeah, so 101, 121. Cool. So yeah, I guess what we can do is first move all bricks down. Then we can find which bricks are find the bricks that can be disintegrated. Yeah. Cool. So, this might actually make more sense to be doing in one single loop. So I'm thinking, I mean, obviously we'll have to move these bricks down. Can we sort them by the minimum Z component? Is there any case where we have to move it a higher brick before a lower brick? I don't think so, because we don't have like a say a brick that was like this shape or it's hanging over. I think we can sort by the lowest Z component. So right now, we're actually sorted already, but that's probably not the case for the full input. Yeah. Um, so bricks.sort key is equal to lambda um, brick to minimum of brick 0, 2, b 1, 2. And then what if we just see if this actually working, we're just sort. This is shuffling it all up, and we actually sort it. It's fixing it. Okay, cool. So this is the order that we want to process the bricks. Um, how big are the bricks in full input? Seems like they're all pretty small. So I think what we want is we want a map that maps um, xy to the brick um, the brick basically maps xy to the max height at that position. Um, so let's grab a default dict. Here, I guess I should use this functionality more. Um, that's a default dict is equal to default dict. So that the input is going to be an xy point. And then the output will be int. And then we have default dict lambda where we map to 0. Because that's the height of the, what is this mat about? Cannot be signed. Uh, what is this mat about? Python create a default. So here, let's just add like a to-do should also store the block at that height. Yeah. What is this map at? Okay, whatever. Alright, I'm just gonna step away for a minute. I'll be back. Alright, we're back at it. Um, yeah, let's do it. Now we can iterate over brick and yeah, x1, y1, z1, x2, y2, z2, and bricks. X min is equal to min x1, x2, y min. I think we're gonna also want x max. We're also gonna want y min and y max. Y min and y max. And finally, z min. I don't think we need z max though. Actually, probably. Okay. So now we can, the range that it covers, so max height equal to 0, and then for x in range x min, x max plus 1, for y in range y min, y max plus 1. If height if height xy is greater than max height is equal to x xy. And then inside here, we're going to do a little bit more logic to track the blocks. And finally, we'll move the block down. I guess we can just do this range a second time. Max, and just set height xy is equal to, sorry, so the amount we move down is equal to z min minus max height minus 1. And so we'll want to height xy is equal to sorry, z max minus dz. Okay, so the first, let's look at the here. So A and B don't move. This is telling us that A and B don't move. C moves by 1. C moves by 1. That's right. D moves by 1. That's right. It goes from height 4 to height 3. E moves by 2. F moves by 4, 2. G moves 8. Let's go to the bottom at 8, bottom 5, 3. Okay, so that works. So this is now to be max height, comma, block index. Let's see, how many bricks could be safely chosen as the one to get disintegrated? Block. Yeah, so now it's addict point. Or I guess a twofold of int. No, it is a point. Point. 0, -1. Or -1 is the index for the floor. Cool. Just so this is all in the same line. Let's do something like this. Where block index of -1 is cool. And then we're just gonna do everything in one loop now. So um 'h block index is equal to, I guess, brick index. I guess we can call this height map. Height block index is equal to sorry, height map xy if height is greater than or equal to max height, um um supporting bricks, I guess we can just call it supporting. So if height is greater than max height, and then if height equals max height, then max height is equal to height, and supporting equals block index. And then if height is equal to max height, we have place while supporting. And then let's print out and this should be something like this. Do a little enumeration. And then here, as supporting be a set. And this is not supporting, but supported by. 3 is supported by 2 bricks. B and so A cannot be disintegrated because it's supported by 1 and 2, which are only supported by A. And then I guess we need the higher end for forks, which is a map from in the brick index to a set of brick indices. Which maps brick index to supported index set. For I in supported by supports I dot add this I guess can be a default dict add I. And then we can also do for k key value in supports dot items print kv. Let's look at what we have here. So 4 supports 0, 0 supports 1 and 2, 1 supports 3 and 4, Oh, sorry. The stretchy. But I think we're close. We are definitely close. Okay. Let's just make sure that this is all the same. So B and C would fall. Um, mm, B can be disintegrated because 3 and 4 are also supported by 2. Um, I guess we should have a map that like support count, which maps an int to count of bricks that support it. Um, because what's like, I'm just thinking about the logic. What is the logic for when we can destroy a brick? We can disintegrate a brick if for each brick that it supports. Um, uh, I guess supported by can be maledict, which maps brick index to the set of supported by index. Here this needs to be supported by brick, or I guess a brick supported by, and and then we can also do supported by x equals brick supported by the subject of int to set. Okay, so so the question is, which bricks can we destroy? We can destroy a brick if for each brick it supports, if for each brick it supports, that brick is also supported by another brick. So we can do for next and laying bricks. And then for supported index in supports ix if Lang supports Lang supported by supported index is equal to 1 break, else iterate count is equals 1. And then return iterate count 5. Okay, let's run this on the input. 459, that seems too high. Or doesn't, I don't know. Maybe it's right. Alright, cool. That's part one. That was pretty straightforward. Yeah, we'll go over everything at the end, just doing a little bit of cleanup here. Cool. Part two. Disintegrating bricks one at a time isn't going to be fast enough. While it might sound dangerous, what you really need is a chain reaction. You need to figure out what the best brick to disintegrate. For each brick, determine how many bricks would fall if that brick were disintegrated. Okay. Disintegrating any other brick would cause... Okay. This shouldn't be too hard, actually. So I think we're going to want to... Let's first just move this up. And then let's copy most of the code from part one, actually all of it, into part two. And then, cool. So I think all this logic is going to be the same up until here. Up until we determine the number of bricks that would fall for each brick we disintegrate. I guess we can... Here, let's do fall count. Is a dictionary that maps from brick index to the number of what is the sum of the number of bricks that would fall? Cool. Wait, this is gonna be easy. So this maps brick index to number of bricks that would fall if moved. And then we can iterate over index in range. We can go the reverse. So we can just iterate over the bricks reversed. So we can do len bricks -1, -1, -1. This always seems like a little bit too much to type to just go reverse, but whatever. And then at the end, all will turn is sum fall count dot values. So easy. Brick fall count x brick is equal to 0 for um, for supported Ix in let me actually copy this. This if you can actually do fall count brick plus equals fall count supported index plus 1. And then here we can do fall count Ix is equal to fall count brick. 3, that doesn't seem right. Okay, and fall count print KV IC.items. Okay, it is a little bit more complicated because yeah, we can't do it like this. Although this would be nice because if we disintegrate block A, both 3 and 4 are disintegrated. Yeah, okay, that's all right. So now we have to go in order. Yeah. Guess. Do we want to write some kind of function here? Yeah, I think we can do something like um will fall is equal to we're not using fall count anymore, I believe. So will fall is a list. It starts with ix. Then we do for for in range disintegrate index plus 1 bricks. We can do something like if this can be a set if um, if here we have supported by index minus will fall. If not, then so if this is empty, then will fall dot add x, and then total is equal to 0. Total plus equals length of will fall minus 1 because this first block is not falling. We're disintegrating it. Cool. Oops. And then return total. And then let's also print disintegrate index length will fall. Oop. No, that's right. That's right. Because we minus 1. And then, yeah. We'll just run the full input. Cool. Wait, this day was pretty straightforward. I don't know if I just had a good approach, but I'm happy. This was quick. So yeah, let's go through my solution. And we can sort of look at the problem. Yeah, so in part one, we can use the fact, in part one, we're trying to figure out which blocks we can disintegrate without other blocks falling. And so the first step is we need to actually compute where blocks end up after they're falling. And to do that, we can use the fact that if we sort the blocks by their minimum z component, that's going to be the order from bottom to top. So like this is the pre-falling. It's like A has the lowest z component, so we should process its fall first. Then B has the second lowest z component, then C, then D, E, F, G, in that order. And yeah, to process a fall, what we can see first of all, I parse the bricks. I store them as all their coordinates. Then I create this height map where the height map is like sort of if you were looking at the grid from a top-down perspective, it's like what the max height at each XY coordinate is. And in addition to storing the height, it also stores the brick index that's creating that height. So we can see that block A, and then we just loop through the bricks. And yeah, so the way we calculate how far they fall is like onto the XY area that they fall onto. What is like the max height there? And because these are like magic blocks or whatever, so even if like a block is supported by only like one side or one corner, it won't fall. So then in this loop, in this first loop, sorry, we can see that we're calculating the max height over the area that this brick covers. We're also storing all of the bricks that support, all the unique bricks that support it, because that will be useful for calculating the disintegration. We in fact store sort of the inverse map to so supports, so the brick indices that each brick supports, as well as the brick indices that each brick is supported by. Then we update our height map accordingly with the knowledge of this new brick. Finally, we can total up the number of bricks that we can disintegrate. So for that, we simply just loop over the bricks. And what we know that we can disintegrate a brick if for each brick that it supports, so A supports B and C, if A was removed, are there any other bricks that support B and C? So what that trend, because if say for example, so D and E are supported by both B and C. So that means that if we remove either B or C individually, then D and E will not fall. And so, yeah, we can, for each brick, we check each brick that it supports. And then if it's supported by only one brick, then we say, okay, then we can't disintegrate. We break out. If we go through each one of those supported indices and no brick will fall, then we can increment the disintegrate count. And so yeah, that'll do it for part one. Part two, 90% the same in terms of the code at least. We create the supports and supported by dictionaries using the same method. Then what we want to find here is sort of a chain reaction. If we remove a brick, how many are going to fall above it? Where we assume that like if we had for example, a stack like A, B, C, we can think of like this is the Z direction. If we remove A, then B will fall, and then C will fall. So that would be like 3 bricks falling. Yeah, so the way we compute that is we go through each one of the bricks. We create this set will fall, and that's sort of like falling is equivalent to being removed because when a brick falls or is removed, the bricks that it supports will be able to fall. So we create this like will fall set. We initialize it with the brick we're considering disintegrating, and then we iterate over all the bricks above it. So all the bricks with a higher index, and then we check. This is a set operation. This is like set minus. So this essentially checks if the brick that is supported by is if like all of the bricks that support brick IX are in this will fall set, so they've already fallen in this chain reaction, then we know that this brick will fall as well. Then for the total, we take the length of this set, like the chain reaction that will fall, and do -1, because remember, we're adding this disintegrate, the block that disintegrates to this list, but we don't technically consider that falling. So yeah, that's that. Yeah, I thought today was a good problem. Made it through pretty easy. Yeah, I guess the new NeoVim color scheme was the buff I needed. All right, thanks for watching. If you have any questions or comments, leave them in the comment section below. And yeah, see you tomorrow for day 23.